We have spent a lot of time using numerical methods to find approximations to exact numbers. Pi is one example. It is an exact number with an infinite number of digits past the decimal. Therefore, any attempt we make to write it out will only be an approximation, never exact. The good news is, we can find approximations that are closer and closer to the exact value. But the question remains, how close is our approximation to the exact value? One way of quantifying this is to count the number of digits past the decimal that match the exact value. Before we can talk about counting digits, it will be helpful to define these two terms. The characteristic is the number to the left of the decimal, seen in red. The mantissa is the set of digits to the right of the decimal, seen in blue. We covered this in our lesson on logarithms, but here is a good reminder. Notice the pattern if I rewrite the argument in scientific notation. So 230 is 2.3 times 10 to the second power, for example. Conveniently enough, the characteristic is one and the same as the power of 10. That is shown in red. To see why this works, we are going to employ the three laws of logarithms boxed in orange. 2.3 times 10 to the third is a product, so we can split that into the sum of two logarithms. Then we can bring the power 3 out front. That is why the characteristic changes by an integer value anytime we move the decimal place. The mantissa, blue digits, always remain the same when we use a base 10 logarithm. The same rule works for negative powers. The mantissa now looks a bit different because we have crossed over from a positive number to a negative number. Hold on just a moment. You can see here that once we have made the crossover, the mantissa is the same after that. Every time we move the decimal to the left, the characteristic decreases by another unit. Perhaps you already noticed a curious pattern. Where I've underlined 1 0, the characteristic is -1. 2 zeros, and the characteristic is -2. 3 zeros, -3. The same pattern continues indefinitely. So how does this help us out? Well, as we just saw, the negative base 10 logarithm of a number effectively counts the number of zeros past the decimal before we reach a non-zero digit. So if we take the negative base 10 logarithm of the error, then that is like counting the number of digits of accuracy. What is error? Error is defined as the difference between the exact value and our approximation. Let's see how this plays out with an actual example. Take a look at this table. In each row, I have rounded pi down to a specified number of digits past the decimal. The error is the exact value of pi minus the number in the second column, our approximation. The fourth column is the negative base 10 logarithm of error, the number in the third column. Trace your eyes down the fourth column. Notice that the characteristic progresses from 0 to 1, 2, 3, 4, all the way up to 14 without skipping. It exactly matches the first column, the number of digits past the decimal. Now, if you were focusing on the mantissa, the digits to the right of the decimal, then the values boxed in orange would round upward, and our neat pattern would be disrupted. How else could our pattern be disrupted? How about rounding the second column to the nearest digit? Last time we only rounded down. This time it could be rounded up or down, depending. Now look at the fourth column. We get an error message in certain rows. Why is that? Because the error in the third column takes a negative value, meaning our approximation is bigger than pi. The logarithm of a negative number does not output a real number, hence the error message. I have highlighted in green the digits that were rounded up instead of down. Notice in each case that the error in the same row is negative and the logarithm fails to give us a number. How do we remedy this problem? We can change each negative value in the third column into a positive number by taking the absolute value, hence absolute error. Now it doesn't matter whether our approximation is bigger or smaller than the exact value of pi. We can round up or down without problem. Each row in the fourth column has a number in it. No more problems there. However, notice the characteristics underlined in orange. These break our neat pattern. So at the end of the day, this might not be an exact way of counting the number of digits of accuracy. Regardless, it is still pretty good for a quick evaluation of accuracy. Usually it is good within 1 unit of the characteristic, as we see here. So there you have it. That explains a little more why taking the base 10 logarithm of error effectively counts the number of accurate digits past the decimal place. This enables us to quickly get an idea of how close our approximation is to the exact value. Of course, you need to already have an adequate representation of the exact value as a baseline of comparison, but that isn't always an insurmountable obstacle. At any rate, this semi-automated approach is preferable to manually counting how many digits of accuracy you have in each row of a data table. Do you have any other ways to quantify the accuracy of an approximation? Let us know in the comment section below. If you enjoyed this video, please share it with a friend. I appreciate your support and look forward to seeing you again.